So we've talked a little about the magnitude system and how it characterizes both the apparent and absolute brightness of stars. Now, once you can see stars, the other thing that you notice is that they move. They change their position on the sky, and they do this for a variety of reasons. But one very important reason is that they change their apparent position because the Earth is moving. And we can use that with some very simple trigonometry to directly measure the distances to the nearest stars. This is the only direct method of measuring distances to stars, so it is enormously important for the field of astronomy.
So parallax is a familiar phenomenon to us. Simply put, if one has an object that is close to us, like this lamppost here, and an object that is further away from us, like this building in the background, and you move a little bit relative to the lamppost, then what you see is that the position of the lamppost relative to the background object changes. If you know how much you've moved, and you measure the angle between this foreground object and the background object, you measure the change in the angle between them, the angle subtended at your eye, then you can use simple geometry to figure out the distance to the lamppost. So we can apply this idea to measure the distances to close-by stars. Here's how it works. On the left here, the white circle is the orbit of the Earth around the orbit of the Sun, which is depicted by the small circle with a dot in it in the center here. When the Earth is on one side of the orbit, it observes a close-by star, the yellow star in the center, relative to a bunch of distant background stars, these white stars over here on the right. When the Earth is in that position, what you'll see on the night sky is that the yellow star occupies this position. 6 months later, the orbit of the Earth takes the Earth to the opposite side of the Sun. Now, you observe the close-by star relative to the distant stars in this position here over on the left. So the distant stars, being distant, have not really changed their positions relative to each other, but this nearby star appears to have shifted. And then as the Earth continues orbiting and we get back 6 months later to where we started, this star will shift its position back again to its original position. And so as the years pass, the star will just shift backwards and forwards relative to the positions of the distant stars in the background. And we can measure the angular distance on the sky that this star moves. And half of the angular distance that it moves in the course of 6 months is just this angle here, depicted in this picture. Here's the same picture with the orbit of the Earth expanded a bit so we can see what's going on a little clearer, and we can do a little simple geometry. So here we have the nearby star and then the collection of background stars at the top here. D is the distance from the Sun to this nearby background star, and if we connect a line between the Sun and the Earth, and a line between the Earth and the background star, then we have a right-angled triangle, the base of which is 1 astronomical unit long. Parallax angle of the star is defined as this angle here, P, which is half of the total angle that we see the star move relative to the background stars in the course of a 6-month period. So simple geometry says that the tangent of this angle P is just equal to the opposite side of the triangle over the adjacent side, so 1 astronomical unit divided by the distance d to the nearby star. Now, as you'll remember from last week from the scales of the universe, the distance to even the nearby stars is enormously greater than 1 astronomical unit. And so this angle P is always going to be very, very, very tiny. And if you remember your small angle approximations, if the angle P is very, very small, and P is measured in radians, then the tangent of the angle P is approximately just equal to P. So the formula simplifies to P is equal to 1 astronomical unit over D, and therefore D, the distance to the star, is just 1 astronomical unit divided by the parallax angle in radians. So measure the parallax angle, and we can measure the distance to the star. Now, at the moment P is in radians. Just a reminder, 1 radian is about 57.3 degrees. But as I mentioned, even the nearest stars have very tiny parallaxes. In fact, the angles that we measure will be tiny fractions of a degree. And the most convenient unit to measure these small angles in is actually a unit called arcseconds. So what's an arcsecond? Well, there are 360 degrees in a circle. An arc minute is defined as 1/60th of a degree. So there are 60 arc minutes in 1 degree. And then an arc second, there are 60 arc seconds in 1 arc minute. Arc seconds are denoted by the 2 apostrophes up here, 60. So this is 60 arc minutes. So in other words, there are 3,600 arc seconds in a degree. So an arc second is 1/3,600th of a degree. So 1 radian is 57.3 times 3,600 arcseconds, and that's equal to 206,280 arcseconds. So if we measure p in arcseconds, then this formula reads that the distance to the star is 206,280 astronomical units divided by the parallax angle measured in arcseconds. This allows us to define a convenient unit of distance. We can define a unit of distance such that any object at that distance from the Sun is going to give a parallax angle of 1 arcsecond. So if we plug that in, p is equal to 1 arcsecond, that distance is 206,280 astronomical units. And we call this unit 1 parsec. Parsec literally means a parallax angle of 1 arcsecond and is abbreviated to PC. So 1 parsec is 206,280 astronomical units. So if we want the distance in parsecs, the formula becomes very simple. The distance to a star in parsecs is equal to 1 over the parallax angle measured in arcseconds. So, for example, if we observe a star in the night sky to have 0.55 arcseconds of parallax, then the distance to that star is just 1 over 0.55, which is 1.81 parsecs. 1 parsec is equal to about 3.26 light years, so this distance is about 5.93 light years. In the homework problems, you'll have a bit of practice just using parallax and distance and converting between the various units. One question that you'll be asked to do is calculate the distance to stars A and B in these two pictures that are observations of the two stars taken about 6 months apart. Our most comprehensive catalogue of the distances to nearby stars comes from the High Precision Parallax Collecting Satellite, otherwise known as Hipparcos, which was launched by the European Space Agency and operated between 1989 and 1993. This satellite measured precision parallaxes of the nearest 120,000 stars to the Sun, precise enough to measure parallax to within milli-arcseconds, to within thousandths of arcseconds. That's millionths of a degree. So these are very tiny angles. Here's a picture of the satellite before launch. The method of parallax is the first rung on what is known as the cosmic distance ladder. As we'll discover, there are a succession of methods of measuring distances to objects in our universe that allow us to measure distances to further and further away objects. Parallax gets us on the ladder in the first place. It gets us to where we can measure the distances to the nearest 10 to the 5 stars. And then we can use the properties of those stars to figure out ways of measuring distances to further objects. It isn't possible to use ordinary parallax to measure distances to stars that are further away because their parallax angles are just too small to observe, even by our most sophisticated satellites at present.
But stop the press. In 2013, the European Space Agency launched Gaia, which is the follow-up to Hipparcos. And just earlier this year, there was a major data release from the project. Its mission was to measure the parallaxes and therefore the distances to the nearest billion stars. And you're going to watch a couple of videos about the Gaia mission, which go into some of the details of why measuring the distances to stars is so important and the huge variety of practical and fundamental astronomy that can be done with these measurements. So in fact, parallax actually allows us to get the distances to the nearest billion stars as of April 2018.